Quaternions are defined as members of a non-commutative division algebra of a more general class of hypercomplex numbers. Okay, that's a lot of words, but what does that mean? Let's start at the beginning. I, j, and k are imaginary numbers such that I squared, j squared, and k squared equal -1, respectively, and such that ijk equals -1. Keep in mind, these are all different imaginary numbers despite all being the square root of -1, because quaternions exist in multiple dimensions. More on that later. Also, quaternions are rotated around a vector. In case you need a refresher,
a vector is a mathematical quantity represented by an arrow with both direction and magnitude. Oh yeah!
Axes that you can rotate something around. These are based on Euler angles, and the axes are labeled alpha, beta, and gamma. However, if two of these axes interlock, then motion is severely limited. This is called Gimbal lock. Quaternions solve this problem. Quaternions operate using the idea that each object has 4 scalar variables because it exists in 4 dimensions, 1 real one and 3 imaginary ones. Because of this, the axes do not interlock at any point. As you might imagine, this has a lot of implications for coding. Here's why. Quaternions are written in this form, with the letters representing real numbers and the imaginary numbers still being I, j, and k. We can multiply quaternions to get what's called a cross product, as long as we remember that ijk equals -1. But unlike algebraic multiplication, multiplying quaternions is not commutative. Here, -1 is equal to a 360-degree rotation rather than a 180-degree rotation like it is otherwise. Therefore, if I make a quaternion completely negative, the value is the opposite, but the rotation is the same. As this 4-dimensional simulation shows, the functions I, j, and k have been rotated such that the values are negative but the orientation is the same. These pictures display the same points, adding 1 dimension each time. The addition of a 4th dimension with a w-axis immensely extends modeling capabilities, as these pictures show. Adding this dimension allows us to more accurately depict design differences such as solar panels for homes, offices, and shelters. Any point may be written as a quaternion. To rotate a point in coding, then, the quaternion must be put into this equation, with theta being the angle of rotation, say 30 degrees. Today, quaternions are more important for their mathematical applications rather than as a concept of their own. When William Rowan Hamilton developed quaternions in the 19th century, there weren't very many fields to use them in. But today, quaternions have become increasingly important to coding and online design, as well as all fields and projects that use said designs. This is just the beginning. Who knows what we can do with quaternions